Hello everyone, let's start solving the next 5 questions for the Jan 2022. So the first question says, I am solving only the organic part, okay. So the first question says, the major product formed in the following reaction is, so you are having this molecule and you are reacting with NaCN. So NaCN, you know, NaCN has Na plus and Cn minus. Now Cn minus is a very powerful nucleophile. Why? Because carbon has negative charge. Carbon is not electronegative at all, so it will not hold the electron close towards itself. So it's a very large lobe with lot of negative charge, so it overlaps very well. It's a very powerful nucleophile. So this nucleophile will go and attack, on the carbon which has leaving group. So this OTS is a good leaving group. You can see oxygen is more electronegative than carbon, so it polarizes this carbon. Oxygen has negative polarity, carbon has positive polarity, and therefore this carbon it will attack and OTS leaves and you get the reaction. Now Cn minus is powerful nucleophile, so it will undergo SN2 reaction. If it is not very powerful, it will stay for the carbocation to form, but it is powerful nucleophile, so it will go immediately and attack and we get this. So we know once SN2 reaction happens, there will be inversion of configuration. There will be inversion of configuration. So ideally the product will be this. The product will be pH will be here, Me will be down, and then top part we are not touching. So top part remains same. Okay, top part remains same. There is no change in configuration. Whereas down what happens? Inversion of configuration happens. So OTS is on right side, so Cn will come on the left side and H will go on the right side, because the coming Cn group will push the hydrogen to the other side. So this is what is the product formed, but you understand there is no double bond, there is no rigidity. It can always rotate and give you different conformer. And that's what they are testing, that do you understand conformers or not. So let us go step by step. So option A, you see there is change of configuration because pH is on top, same as here, and this place Me has gone on right and H is on left, but this configuration should not have changed. So clear cut we can forget of A. Similarly on B also, you see on the top again there is a change of configuration. B cannot, on the top there is no change of configuration, so you can forget of B. We need not even look at down. Now what we need to look is basically now C and D. So C and D, let us see what happens. In down, Me is there, so Me is here also, okay. And then what happens? H is on the right side, Cn is on the left side. So H is on the right side, Cn is on the left side. So here configuration is different from the product, so the configuration remains same as the reactant. So OTS leaves, and if you get same configuration, that means something is wrong. So this does not look right answer. C looks right answer to me, but let us confirm it. So here configuration not changed, so configuration has changed and we are getting the configuration of the product. Let us see on the top if we are having same. So there are two ways to look at it. One easy way will be if I find out the absolute configuration and then verify, or I will just see the arrangement of the three-dimensional arrangement of the substituents. So let us look at this carbon. So what does this carbon show? The vertical line means away from the viewer and horizontal line means toward the viewer. So this bond is there, this is in the plane, we don't worry about that. What we are worried about is this. This is the pH, this is the pH, this is the H, this is the H, okay, and what we have behind is Me. And what we have here is this. So this bond is here and this H is on top, Me is also on top, towards the viewer, and this pH is away from the viewer. Now we have to find out if they both are saying same thing. So the angle between them, see it's a sphere, a circle, so the angle will be total 360, so each of them angle is 120 degrees. Now if I rotate, I will keep this as constant, I will check if this is same. So I will rotate in such a way so that pH goes away from the viewer. This pH goes away from the viewer because here pH is away from the viewer, and we see if it is same. So if I rotate 120 degrees like this, then what happens? pH goes in the place of Me, Me comes in the place of H, and H goes in the place of pH. So what do we get? We get is pH, what we get is pH away from the viewer, okay, and then what happens? H come towards in the right side, right? H come towards in the right side, and Me goes towards in the left side. Me goes in to the left side towards. Now you can see that this and this are same, so we are damn sure that answer is C. Another way will be to look at the absolute configuration. Okay, let's look at the absolute configuration also for the product formed and see if C is the right answer. So what we saw? We saw that product is this. Let us look at the product. Yeah, this is the product. Okay, so let us look here. This is the chiral carbon. Let us give absolute configuration on this. So it has 4 bonds. One is leading to hydrogen, this is to carbon, this is to carbon, this is also to carbon. So we give absolute configuration according to CIP rule. CIP is Cannon-Ingolf-Prelog rule. We go bond by bond and look at the atoms and look at the atomic number and decide. So here first, when the first atom is carbon, which is forming benzene ring, here the first atom is carbon, which is having 3 hydrogens attached to it, and here is another carbon which is attached to hydrogen, carbon, methyl, and here is hydrogen. So all 3 are carbon, so there is doubt. Fourth one is hydrogen, which is least atomic number, so this has to be the 4th priority. Now what about this? Here carbon is attached to, when it is a phenyl ring, it is a carbon, double bond carbon, and another carbon here this side, right? That's how is the phenyl ring. Then you have here, and then you have here, and then you have here, right? And you get double bond here, and here hydrogen is there. So a double bond will be considered as 2 different bonds. So we can say this carbon attached to 2 plus 1, 3 carbon atoms, whereas this carbon attached to 3 hydrogen atoms, and whereas this carbon attached to 2 carbon atoms. So clear cut phenyl gets the higher preference than this one and this chiral carbon, and then so this is the second priority, phenyl ring is the second priority, this is the 3rd priority, and methyl gets the 4th priority. Okay, so we can put it here, and we can say this will be your 2nd priority, this will be your 3rd priority, and this will be your 4th priority. This is the CIP rule, because we are going first bond for both of them is carbon, but this carbon attached to 3 carbons, whereas this carbon attached to 2 carbons and 1 hydrogen. So hydrogen, will forget it, we always look at the next atom which is highest atomic number. So this is having 3 carbons, whereas this is having only 2 carbons. So this gets lower priority, that is 3rd, this 2nd, and this has no carbon attached to hydrogen, so this gets 4th priority, sorry, 3rd priority. What am I doing? Sorry, this is 1st, this is 2nd, and this is 3rd, and that one was 4th. I somehow got confused between 1st and 4th. Okay, so this is 1, 2, 3, and 4. So let us look how will be the rotation. So we forget about the 4th, we only see the spatial arrangement of 1, 2, and 3. So 1, 2, and 3 is going in the clockwise direction, right? In the clockwise direction. So if it is clockwise direction, it is R, absolute configuration is R. If it is anti-clockwise, it is S. But another thing to remember is the lowest priority should be away from the viewer. But in the Fisher projection formula, this hydrogen, that is in horizontal line. Horizontal line is towards the viewer. So hydrogen, the lowest priority should be on the vertical line and not on the horizontal line. So if it is on the horizontal line, whatever it looks like, we'll be writing opposite of it. So here the configuration looks like R because it is clockwise, but it will be S on this carbon. Okay. So we'll delete this and we'll just remember that on this carbon, if I mark it as carbon number, if I mark it as carbon number 2, on the carbon number 2, absolute configuration is S. Okay. And let us look at this. On this carbon, what is there? So on this carbon, we are having 4 bonds: carbon, 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 and hydrogen. So straight away hydrogen gets 4th preference. Now here there is carbon attached to 3 hydrogen. Here carbon attached to triple bonded nitrogen. That means this carbon attached to 3 nitrogen atoms, whereas this carbon attached to 2 carbon and 1 hydrogen. Now nitrogen has more atomic number, so even if it was single bond with nitrogen, this would have got more preference. So CN gets 1st preference, this gets 2nd preference, and this gets 3rd preference. Again hydrogen is on horizontal line, so whatever you get, we'll write opposite of it. So we'll look at only 1, 2 and 3. So 1, 2 and 3, it is going again in clockwise direction. So it looks like R, but it will be S. So this is what we are getting the product. Both the configuration should be S. Now let us look here if we are getting same as S or not. So here again phenyl, we saw phenyl gets the 1st preference, then this chiral carbon gets 2nd, and then methyl gets 3rd, and hydrogen gets 4th. Hydrogen is on horizontal line, it should have been a vertical line, so we'll write opposite of what we get. So see, 1, 2 and 3 is in clockwise, so looks like R, but it will be S. Okay, so it will be S. Now let us look at the second chiral center. On the second chiral center again, CN gets the 1st preference, this gets the 2nd preference, methyl gets 3rd preference, and hydrogen gets 4th preference. And hydrogen is again on horizontal line, should have been vertical. So 1, 2 and 3 are arranged in clockwise direction, so looks like R, but it will be S. So very clear, we are 100% sure that the answer is C. Moving on. Question number 7. It says an organic compound with the molecular formula C9H10O2 exhibits following spectral characteristics. These are there. IR is 1720 per centimeter, the most probable structure. Generally you should always whenever such question is there, find out what is the unsaturation index, and that gives you how many unsaturation index was there. But this was extraordinary simple question, so I did not do. You also need to find out that do we really need to do. Why? Because if you look here at delta 9 we have a signal. So delta 9 generally around 10, we get CHO, aldehyde CHO, it shows up. Also IR is showing at 1720, 1725 per centimeter is for C double bond O stretch of aldehyde. So it's almost very clear it's aldehyde. Then what else we look? We look that it is having signals around the region of 7.1 and 6.7. So it is having aromatic ring. So all of them are having aromatic ring, but this is having ester, and this one is also have so this can be neglected. Why? Because ester will always show around 1735 in the aromatic region, and no proton in the ester is there which will show up around 9, okay, 9 or 10. It was not 9, 9.7, it is around 10. Aromatic region will be around 7, maximum it can go up to 7.5. So this can be neglected. Now the competition between B, C and D. Okay, so let us look at the structures. This is the aromatic region. In aromatic region we can see only 2 peaks are there. So if you look at aromatic range, okay, aromatic peaks, when it is disubstituted, you can see in all 3 of them it is disubstituted. So if the substituents X and Y are in ortho position to each other, then how many peaks will be there? See, this hydrogen and this hydrogen are different very clearly. Even this hydrogen is different from all others, and this hydrogen is also very different from all others, because this hydrogen is 1 bond different far from X, whereas it is 2 bonds difference from Y. Similarly, you can see, so it should give 4 peaks. So it is definitely not ortho disubstituted product. Let us look if it is on meta position, what happens. So that means at ortho position you are having H, and at meta position you are having Y. Y is another substituent. Now what happens? This H will show 1 peak, and this hydrogen is again different from this hydrogen, and again this hydrogen different from all. So again this should also show 4 different peaks. Whereas if the two substituents are in para position, then what happens? If the two substituents are in para position, then see this hydrogen and this hydrogen are identical, chemically identical. See, it is 1 bond far from X, this is also 1 bond far from X, it is 2 bond far from Y, and this is also 2 bond far from Y. So these two hydrogen will show 1 peak, and similarly these two hydrogens will show 1 peak. So basically it should show only 2 peaks, which are seen here at 7.1 and 6.7. So very clearly it should be para disubstituted molecule. Let us look what are the para disubstituted molecule. So there are two para disubstituted molecule, one is B and one is C. We can neglect of D. Now between B and C we have to find out. So we are having OMe and we are having CH2CHO in C, and here we are having OMe, CH2 and then CHO. Let us look. So now what it says is around 3.8, it's quite high value, okay, for proton NMR. That means beside it has to have a heteroatom. So it is singlet 3 protons. Singlet 3 proton means very clearly CH3 is there, and besides CH3 there should be something which does not have hydrogen, so something like oxygen, because quite high, and we know only the oxygen is the heteroatom here. So this is OCH3. Okay, so let us look here. This also looks right to me, this also looks right to me. Now if these two hydrogens are there, they may not split this CH3, because CH3 is next to oxygen. Oxygen does not have any hydrogen. So this looks okay to me. Okay, both of them look right to me. What happens next? Next is 3.6, little lower but still quite deshielded. Doublet 2 proton. Doublet and 2 proton. So doublet 2 proton. So if this is CH2, this will show 2 proton signal, but will it be doublet? No, because if this hydrogen did not split this methyl, how can this methyl split this CH2? So B doesn't look right to me. Let us look here. So if this CH2 is there, beside this CH2 there is a carbon which has a hydrogen, one hydrogen, this aldehydic hydrogen. This will split this CH2 into doublet. That means this aldehydic hydrogen also should have been split as a triplet by this CH2. So let us look at it. So here you see this has been split, the aldehydic proton has been split as triplet, and this hydrogen has been split as doublet. So C is the answer. C is the answer. Whatever I said, I have written here. I am sorry, I went quite fast with the previous question. I will go very slowly so that you read whatever I have written. Please pause it and read it if you are not able to read fast. So I will go slowly, okay. Now this second question just now which we discussed, everything I have said is written here, okay. So the answer is option C. Moving on to the next question. The major product formed in the following reaction 2S3R 2-chloro-3-phenylbutane with NaOET in ethanol. So first thing is they want you to draw this molecule. So you can see there are two chiral centers 2S and 3R 2-chloro-3-phenylbutane. So let's first make butane 1, 2, 3, 4. Okay. Then you have to have chloro. So first what I did, how I made the structures, first I put hydrogen behind because that's what is expected. If you want to know absolute configuration, the lowest priority has to be away from the viewer. So what I did is I put hydrogen behind and it says 2 chloro. So at position number 2 I put of chloro towards the viewer, and it says 3 phenyl. So at position number 3 also first I put hydrogen away from the viewer, because that will give the right configuration. The lowest priority has to be away from the viewer, and I put phenyl towards the viewer, and I checked, and interesting, I got opposite configuration of what is asked for both of them. So I just change the configuration. So let us look at this molecule. So this is 1, 2, 3, 4, because chloro is there, so you count from this side, and that's why it says 2 chloro. Okay, so now let us look at the absolute configuration. So hydrogen is away from the viewer, so that's excellent. Chlorine will get first preference because chlorine has a higher atomic number. Now this is methyl, this is carbon. So this carbon attached to 3 hydrogen, whereas this carbon attached to 2 carbons. So this gets second preference, this gets third preference. So now we look the 3-dimensional location of the substance 1, 2 and 3. So 1, 2 and 3, they are in clockwise, so it should be R. But the question says 2S, and therefore I reversed the thing here. So I put H front and Cl behind. Similarly, you look here. So on this hydrogen gets fourth preference, no doubt about it. Let me just rub other things to remove the confusion. Okay, so now let us look here. So here the first preference comes to here it is carbon, here it is carbon. Now this carbon attached to 3 carbons, whereas this carbon attached to chlorine, carbon and hydrogen. So we always look only at the highest atomic number. So this carbon attached to chlorine, which atomic number is 17. Here all are just carbon. So this gets first preference, this gets second preference, this gets third preference, and this gets fourth preference. Now we have to look only at 1, 2 and 3. So it is like this. So it is like this, right? So it is anti-clockwise. So it looks, it is S, but what they have asked is R. So that's why we had to change, and then we had to put H front and pH behind. So this is your product. Now it says what you are adding is sodium ethoxide in ethanol. This is very interesting question. Now we can think of 2 ways. The sodium ethoxide means basically we are interested in OET minus. Now OET minus can act as a base. It can also act as a nucleophile. So you can think that OET minus will attack this and Cl minus leaves. Okay, and then you get SN2 reaction. So that will be one way to look at it. Another way to look at it, OET minus takes away this proton. You can see it is anti to this Cl. Cl is away from the viewer, H is towards the viewer. So angle is 180 degrees. So elimination is possible. So this goes out and this Cl minus leaves, and you get alkene. Correct? So now the question is, will it act as a base or a nucleophile? And you see the product here, it is acting as a nucleophile. All other place it is acting as a base. So it's a small table, I took it directly from Claydon, which says about what kind of thing, if you have something like this, strongly basic unhindered nucleophile, and then on secondary system it will undergo SN2 E2 reaction. It doesn't undergo SN2, it acts as a base, not as a nucleophile. Another way to understand is this: OET minus, oxygen is having negative charge. Oxygen is quite small. Okay, so it is tough to distort the orbital, so it is hard. Okay, now a hard species will attack hard species. Among proton and carbon, proton is smallest size, so it is hardest. So hard will attack hard, so it acts as a base if there is competition between hydrogen and carbon, because carbon is relatively much softer than hydrogen. Because carbon is much bigger, you can distort it, you can polarize it. So hydrogen is easy to polarize, easy to distort, so it is soft electrophile, whereas hydrogen is hard electrophile. Or you can say carbon is soft base, hydrogen is hard base. Carbon is hard acid and hydrogen is, carbon is soft acid and hydrogen is hard acid, because hydrogen is very small, proton we are talking about, okay. So therefore oxygen, since it is small, it will rather attack hydrogen because hard attacks hard. If it was sulfur, then it would have gone SN2 reaction, but because it is OET minus, it will undergo elimination reaction, and that's what happened. So now very clearly what we want is the hydrogen and the chlorine, they have to be anti to each other. So actually we need not rotate and all, but I have rotated so that if somebody has the issue with stereochemistry, let him understand. Otherwise it's very simple. You can see that this hydrogen is towards the viewer and this Cl is away from the viewer. So if you use a base, it will just go and Cl minus leaves and you get a alkene. They are 180 degree to each other. But still, for the for more clarity, let us put. So let me put Cl on the plane. So I am rotating it 60 degrees. So not 60, sorry, it should be 120 degree. Yeah, it should be 60 degrees, half of it. I am rotating 60 degrees so that Cl comes in the plane. So I am rotating it. It is coming outside the board, right? Outside your screen it's coming, so that Cl comes on the top. So hydrogen goes down, but it's toward the viewer. CS3 goes behind the viewer, away from the screen, behind the screen. Okay, so you get this. Just 60 degrees you are rotating. Okay, rotating 60 degrees. And here also what I want this hydrogen to come in the plane, because I want it to be anti 180 degrees to Cl. So I am pushing it from inside towards inside the screen, so that H comes here and then CS3 comes towards the viewer, pH goes away from the viewer. Okay, and then OET minus comes, attacks here, this goes here, Cl minus leaves, and you are getting this alkene, and you are getting this alkene. Okay, so now is it E or Z? That's what we have to find out. So on the each carbon, this carbon and this carbon you have to look separately. So on this carbon you have to give priority according to CIP rule. So between carbon and hydrogen, of course carbon gets higher priority, so it is 1, hydrogen gets 2. Again here it is phenyl, it is CS3. So both are carbon. Next bond, this is 3 hydrogen, here it is 3 carbon. So phenyl gets first, this one gets second. You can see 1 and 1 are on same side, 2 and 2 are on the same side, so it is together, so it is Z. If it was across, that means 1 and 1 opposite, 2 and 2 opposite, then it would have been E. So the product is Z 2-phenyl but 2-ene. So the answer is yeah, B is the answer, Z 2-phenyl but 2-ene. Okay, go through this. I have written quite well this answer in great detail. See, this table is very interesting. Okay, go through it thoroughly. Right, question number 9. The major product formed in the following reaction. So you are having alpha haloketone. So whenever see at alpha haloketone and you are using a base, remember this is Favorsky rearrangement. Okay, and so it's alpha halo on the both side. That's very interesting. So when you use NaOMe, again just now we saw, first it acts as a base rather than as a nucleophile. So it will pull away proton from the neighboring carbon, because the neighboring carbon hydrogen is acidic to a certain extent, because if you remove this proton you get a negative charge, and negative charge is quite stable because it is stabilized by minus R effect of C double bond O, is stabilized by conjugation. That means it doesn't mind losing proton, because even after losing proton it is stable, and therefore this proton is acidic. So now very clearly we have to see which proton will be removed. On this carbon there are 2 hydrogens, on this carbon there is no hydrogen. So this hydrogen will be removed in the first step. In the first step this hydrogen will be removed, you get negative charge which is stabilized, and then that goes and forms 3-membered ring. Now 3-membered ring is kinetically very favored, but thermodynamically very unstable. Kinetically means very fast it forms, but it won't stay like that, it is quite unstable. So it immediately goes and attacks this Br minus leaves, you get this. Now OMe minus goes and attacks. Now OMe minus goes attacks and you get this O minus, and then when this comes down, one of the bond will break, either this one or this one. Which side will break? It will break this side, because if you get a negative charge here, this negative charge is stabilized by this bromine. Whereas if it leaves here, you are getting negative charge where both are methyl group, both will pump electron and will destabilize the negative charge. So bond will break on the right side and not on the left side. You get negative charge here. This negative charge takes proton from the solvent as methanol, and you get this product. So the answer is option B. Okay, so the answer is option B. Last question for today's lecture. It's a very simple question. The reactivity of enol derivatives towards benzaldehyde. So basically benzaldehyde is your benzene ring. On that you are having CHO. Okay. So this is having positive polarity. Oxygen is more electronegative than carbon, so electrons are closer towards oxygen. So carbon has positive polarity and oxygen has negative polarity. So this will go and attack. So oxygen will not attack. Oxygen, what happens? Oxygen will pump electron so that this carbon will go and attack, because carbon is more nucleophilic than oxygen. Oxygen holds electron close towards itself, so it's not happy to give electron. So rather carbon is not electronegative, so it will always pump. So basically whichever is more ionic, that will donate electron more better way than which is more covalent. So if it is covalent, they will start sharing. So when is the maximum ionic character? When there is maximum amount of electronegativity difference. So between oxygen and lithium, oxygen and silicon, oxygen and zinc. So lithium is most electropositive. So oxygen electronegative, we know that. So we have to look at the electropositivity. Metals by definition, they are electropositive. That means they give electron to get positive charge. So metallic character we define by how much electropositivity is there. Okay. So lithium is very strong metal because very electropositive. Then comes zinc, and silicon is non-metal, so it's not electropositive. So they will form almost covalent bond, difficult to break it. So therefore the first will be this, second will be this, third will be this. So highest is 1, then comes 3, then comes 2. So D is the answer. Okay, that's it for today. Thank you very much.